I was going to talk to you something about classification. And in my previous presentation, I talked two methods for the classification. The first one is a discriminant function for classification, and the second one is a discriminative model for classification, such as obvious regression. And today I will talk the third method, generative model for classification, such as Gaussian determinant analysis. And first one, let us have a quick recap of the first two methods. And for the first one, we just use a function, and given any input x, then we output a function value y of x. If y of x is larger than here we only consider binary classification. So if the output is larger than 0, then we report x belongs to the first class, otherwise it belongs to the second class. So for the first method, we have x star argument 0, then x belongs to the first class. Less than 0, then x star belongs to the second star. And if x star equal to 0, then this is on the classification boundary. So to solve this problem, we just use on this square method and take the first order derivative one equal to 0, then we can get.
C1, C2?
C1 is the first class and C2 is the second class. And then something like this. Yeah, here T is the input label, classification label, and X is the input vector. And by solve this square and minimize this square, we can get a solution like this. And I will give you a geometric interpretation about this function yx. And as we see, what's the omega and what's omega 0, and what's this yx in a geometric perspective. So let's first draw a picture here. We can see there are a two-dimensional case. So we have x1 and x2 here. So x here, the input x is two dimensions. It contains x1 and x2. So if we set once 0 equal to 0, then this is a one-dimension I, right? So for any given d-dimensional data, then we can have d minus 1 hyperplane to linear separate the input vector x, and then we can do some classification. And suppose we have a y like this. This is y equal to 0. Y of x equal to 0. And in this region is y bigger than 0. And in this region is y of x less than 0. And so this part is C1 and this part is C2. And first let's see what's the omega here. And suppose we have a two vector here, xa, xb here, and xa here, on the classification boundary, right? So in this case, we have two vectors. So we have y of xa equal to omega transpose xa plus omega 0 equal to 0, since this vector is y on the classification boundary according to the definition. And we have a y of xb equal to 0, right? So we substitute the second by the first equation. We get omega transpose times vector xa minus xb equal to 0. So here is a dot product. This is a vector of omega transpose, and this is vector of xa minus xb. So what's xa minus xb? It's here, right? Here is a vector xa minus vector xb. It's a vector here. And we see the dot product equal to 0, which means the vector omega is orthogonal to this vector, right? So the vector omega indicates the direction of the classification boundary. So this is a geometric meaning of omega here. This is the direction of y-axis. Any questions about this one? So let's take a second look. What's the omega 0 here? Okay. Suppose we have a vector x on the classification boundary. And here is the vector of omega. And the distance from the origin to the classification boundaries, we define as r here. So what's r? R is equal to the magnitude of x, right? Magnitude of x, this vector. This vector is on the classification boundary times cosine theta, right? So this is the distance from the origin to the classification boundary. And so what's cosine theta? So the dot product between the vector omega and x is equal to the magnitude of omega and x plus cosine theta. So we can see the cosine theta is equal to the calculate. Then we can cancel this term, and we get the distance equal to something like this. And we substitute y into this equation here. Is equal to y of x minus omega 0, or the magnitude of omega. So here x is on the classification boundary, so y of x equal to 0, right? So we get the distance from the origin to the classification boundary is minus omega 0 over the magnitude of the vector omega. So
R is the distance?
yeah, r is distance. It's the distance from the origin to the classification boundary is this f. So according to this, we can see omega 0 given the threshold or distance, how far the classification boundary away from the origin, right? So here is the threshold. So we can change omega to change the direction of the classification boundary, and change omega 0 to change the bias and how far the classification boundary away from the origin. So by control both parameters, we can adjust the classification boundary. So this is the geometric interpretation of this two vectors. So as we see, what's the y of x here? in this case, we have a arbitrary vector x is not on the classification boundary. Then we make a orthogonal projection of x onto the classification boundary. So we have x orthogonal like this is a perpendicular projection of the x on the classification boundary. Here is the, we use this notation, x orthogonal. And
which one is whatever y is equal to?
x orthogonal is a perpendicular, is an orthogonal projection of the vector x onto the classification boundary. So, for example, here
Yeah,
we have a vector x and we have a vector y. The perpendicular projection is y prime here. So this is the perpendicular projection of x here. And if we represent the vector x in terms of the x perpendicular, then we get x. Here is the x perpendicular, here is x, and then here is another vector, right? So we call this vector like x prime, okay? This vector like x prime. So x equal to x perpendicular plus x prime, right? But so what's the x prime here? We can decompose the x prime into two components. Suppose this length is R1, and the length of this part is R2. And the direction of this vector is omega over the magnitude of omega, right? This is a unit vector, indicates the direction of this vector. So in this case, x prime equal to R1 plus R2 times a unit vector. Here is R1, here is R2. So what's R1? I just show you R1 is the activity of omega 0 over the magnitude of omega. It's R1. And what's R2? We don't know, right? So we try to get what is R2 here. And what else? So far so good, right? There's no more questions. And if we multiply ohmic transpose on both sides, then we get ohmic transpose x equal to ohmic transpose x perpendicular plus both to are scalar, right? Transpose plus R2. Okay, this is minus. There's a minus sign, so this is minus. We just multiply ohmic transpose on both sides. This is a scalar. This is a unit vector.
Oh, I think you missed the prime.
Yes, there should be a. There should be a.
Yes, it's here. Oh yeah, sorry. Okay, sorry. Yeah. Right.
How matters outside.
Oh yeah. something like this, right? And what's the Hoping transport volume? Is equal to square, right? So this term is equal to the magnitude of volume. And we expand this term. And what's this? This is y of x minus omega 0, right? This term. And what's this? This is equal to 0, right? Yeah, because they are orthogonal and perpendicular. So this is equal to 0. And we expand this product is equal to minus omega 0 plus R2. Right? So the minus omega 0 was cancelled, there's a 0. So finally we get R2, here R2 equal to y of x over the magnitude of, right? What's R2? R2 is the distance from the vector x to the classification boundary. So we got the function output y of x is on a geometric graph is the distance from the input vector to the classification boundary. So this is a geometric interpretation of this discriminant function method for the classification. So any problems?
How do you get W again?
Oh, you mean that? Oh, yeah. You just use this mean method, this square.
Okay, here, this square only consider one. It consider only like one label.
Yeah, yes, we are consider the binary case. We only have binary label, yeah. But the input x can be multi-dimensional. In this case, x is two-dimensional, so we have a one-dimensional line. If x is d-dimensionality, then we have a d minus 1 hyperplane. So I just want to show you a way how to interpret each parameter in this discriminant function on a geometric graph. This controls the direction of this classification boundary. And this is a threshold or a base control how far this classification boundary away from the origin. And here the output, just how far the input vector away from the classification boundary. So, no problem. So the second one is called the discriminative model, and the third is the generative model. So what's the difference between the last two? Both of them try to solve the posterior distribution, PT given x. Here T is the classification label, x is input vector. And we can see the first just gave output of a function, and if it's bigger than 0, then we said it's belong to class 1 or belongs to otherwise belongs to class 2. In the last two, there are probabilistic model, right? So this is different between the first and the second two. And in both of the last two, we try to solve the posterior distribution of T given x. The difference between the second and the third is we directly solve this posterior distribution without evaluating the joint distribution of Tx. And in the third method, we try to evaluate the joint distribution to get the posterior distribution. So So let's review, give a quick recap about the second method. So we try to solve the posterior distribution of PT given x. Then it can be, let's see, we consider a binary case. The probability of t equal to 1 given x is equal to, according to the Bayesian rule, is equal to the x given t equal to 1 times pt equal to 1, and over the model evidence. And we can, oh yeah, sorry.
Oh, I mean,
No.
over px.
Yeah, or yeah, I try to explain that. Yeah. So how to get to the model evidence? We just marginalize the joint distribution, right? And in this case, t is a binary, so. Right. The denominator is just the px, which equal to the px. This is the denominator. We marginalize the joint distribution. Since t is a binary, so we can write the denominator on this. And if we divide the denominator on both sides, so we get 1 over 1 plus exponential like minus a. Right. Here a is equal to the p x given t equal to 1 and p t equal to 1 over p x given t equal to 0 p t equal to 0. We divide the numerator on both sides, right? This is equal to 1, and this term divided by this term is also equal to 1. And this is x given t equal to 0 over the probability of x given t equal to 1. And we take the exponential and plus the minus sign here. So we flip the here and take the algorithm here, so it's still a probability of x given t equal to 1 over, right? So last time we call this object. This is an object function. And we call this term the O. This is the O. Right? Why this is O? This is just equal to t equal to 1 given x over t equal to 0 given x. Right? Because they have a common denominator here. If this over denominator and this over denominator, the numerator is t equal to 1 given x. So this is the O's, the definition of O's. Any questions? Right? And in this case, we suppose if we don't want to evaluate this joint distribution, we just simply use a linear model, linear regression model to approximate this function. We use something like this. This is a linear combination of x. And then we can maximum likelihood with respect to this parameter omega. Then we get the obvious regression solution. So the key idea of the discriminative model is just that you have the posterior distribution. You model the posterior distribution of your input with a function. If this function is obvious sigmoid, this is obvious regression. And you can use the prohibit or other functions. So you get different models. So in this case, we didn't evaluate the joint distribution. So the computational complexity of this method is much less than the third method. After I present the third method, you can figure out how much they save the capacity. So far, any questions?
So you need to learn px given t and pt in this model. We need to learn this too.
We don't need to learn this thing. We use A to represent all of them, and we use a linear conditional line to approximate A.
That's discriminant model.
Yeah, this is discriminative model.
So for the generative model, you need to learn this to p.
Yeah. Px given t. So in this case, we save a lot of computational power. We don't need to evaluate. And I will give you a very intuitive explanation about this after I show you the third method. And just keep reminding me. Yeah, maybe I can show you right now in case I can solve. So suppose here is the joint, the likelihood of t equal to 1. Here is the likelihood function of p x given t equal to 1. And here is the likelihood function of p x equal to 0. And what we are interested in is the posterior distribution of x equal to 1 given x, and the posterior distribution x equal to 0 given x, right? And if we know the likelihood function, something like this, so this is a classification boundary map. It's not exact yet. It's something like this. Actually, this point is a classification boundary. And by learning this likelihood function, we can draw the posterior distribution, something like this. Right. This is a likelihood function. This is a posterior function. And we see here is the classification boundary. Right. Given this posterior distribution, we only care about where is the classification boundary.
So is this assuming PT1, PT equals 1 is equal to PT equals 2?
Yeah, you can think something like that. It's a uniform distribution. Yeah. You can assume PT equal to 1, PT equal to 0. Also, you can use the Bernoulli distribution. In this case, I just give you an intuitive way how to interpret this. Why the second method will work without evaluating the joint distribution. Yeah, actually you can use the Bernoulli distribution. There's no big deal.
Only when these two terms cancels out, you can draw this. Otherwise,
what's our question?
I mean, if they are the same, you can cancel them, and then you get the.
I don't need pen. Then what do you mean? In this case, there's no assumption. I just draw the likelihood probability of x given t equal to 1. There's no assumption, right? This is just the likelihood function, and this is another likelihood function. And
yes.
your R can be anything.
Yes, I understand this, but my point was, if we only consider the likelihood function, then make a decision. In that case, we are ignoring the prior probability.
I didn't only consider the likelihood function. I think I just draw the posterior distribution. The posterior distribution can be learned from joint distribution. I just show you the posterior distribution is something like this, and this is what the likelihood function looks like. And of course, you should evaluate the joint distribution to get this posterior distribution. I just show you originally the likelihood function is like this, and finally the posterior distribution is like this. So in this case, if we see this region, there's no contribution, right? Whatever, they can be any shape. And finally, you will get the same posterior distribution. So in this case, we don't need to evaluate the joint distribution. So we can save a lot of computational power and decrease the complexity. So this is why the second method works. Suppose you know the posterior is like this.
Yes.
And you know the likelihood is like this. So there's no contribution here. It can be any shape. Right? So we no longer need to evaluate the joint distribution. We just simply use a linear combination of values to represent this outputs. So in this model, we only have a number of parameters. M is the number of dimensions of the input vector.
So you're saying the discriminant model in this case is better than generative model?
No, I didn't say that. I just in case it's all complexity. Compared with the generative model, it's offer all complexity. It depends on your problem. You need to choose which method is better or not. And I will explain how to choose this algorithm later. So far, any questions? Of course, we can solve this problem by maximum likelihood estimator and get the model practical. So here is suppose x is m dimension. So the number of parameters in the first case is m. In the second case is m. Right? And I need to mention in this case we don't have a closed form solution, so we need to calculate the derivative of omega, right? Something like this. Then we use some iterative method. Here is a Fermi grid. We just take the first order derivative with respect to the log likelihood function and get this derivative of omega. Then use some iterative numeric optimization method to get omega, since there's no closed form solution. In this case, we suppose the distribution of X satisfies a Gaussian distribution, so we can get a closed form solution here. And now I will talk the third method. So we also need to evaluate the probability of t equal to 1 given x. And in this case, we need to evaluate the joint distribution given t. Over the joint distribution here. So what's the likelihood function of this? It's a Bernoulli distribution, right? It's So let me show you what's this. Suppose the probability of t equal to 1 is equal to pi. We use a vacant variable pi here. And the probability of t equal to 0 is 1 minus pi. Since we consider a binary classification. And what's this? In this case, we suppose the likelihood function of this satisfy a Gaussian distribution. You can use different like boson or something, but you should give a distribution to model your program. So here we suppose it's a multi-variable Gaussian, like 1 and covariance matrix in this case, and P0 is 0. And we suppose both of the Gaussian distribution have the same parameters, otherwise there is no false outcome. And in this case, we can write down the likelihood function. So let's first write down the joint distribution, and it's a t equal to 1, x is equal to pi times the Gaussian distribution, right? This is the joint distribution of t equal to 1. And the joint distribution of t equal to 0 is 1 minus pi, and the times the Gaussian distribution 0 and the covariance matrix. And then we can, if we want to maximum this posterior is equivalent to maximum the joint distribution because all the evidence is constant, right? So in this case, we try to maximum the joint distribution. So what's the joint distribution of Px? So it's a bottom distribution, right? So it's pi mu 0, mu 1 sigma t and 1 minus pi 0, 1 minus t, right? This is a joint distribution. In this case, I combine the both cases together.
Here t is
T is
0,
0 or 1.
Okay.
T can be 0 or 1. If t is 0, then we get the second term. Otherwise, we get the first term. Right? So we combine both joint distribution together. And we see maximize this joint distribution equal to maximum this posterior distribution, then the model evidence is constant. And in this case, we introduce the three hidden variables: the pi, the mu1, mu2, and the covariance matrix, right? And then, with respect to those hidden variables, we use maximum likelihood estimator, like t x given pi mu1, mu0. So in terms of t, we maximum the posterior distribution. In terms of this hidden variable, we maximum minus the likelihood. Right? And here t is a vector, can be a vector since we have a bunch of observations. And x is also a vector, it's a bunch of observations. It should be some capital X, like, yeah, maybe there's an bar here, which indicates it's a bunch of observations. And we suppose each observation are independent, so that this joint distribution can be decomposed as a product of all the observations. Like we have total n number of observations. So in this case, we have a Tn xn given pi mu1, mu0, and the sigma, right? And each joint distribution can be given in this formula. And we plug this formula into here. And directly maximum likelihood with respect to the joint distribution is not easy, so we take an algorithm onto this joint distribution and try to maximize the rhythm of this joint distribution. And then if we take an algorithm, the product will be trained to a summation, right? And I will skip this derivative since we have do it many times. And we just give you the answer at t at pi just equal to the n1 or n1 plus n2. Here n1 is maybe n0. Here n1 is number of label equal to 1 and n0 is number of label equal to 0 and n1 plus n0 is equal to n total number of observations. And here the mu1 just equal to n1 over t n max. Here just the mean. And mu0 is n0 1 minus tn x. And the covariance matrix is more complex, so I won't show you here. But
you mean select all the x corresponding to 1?
yeah.
Okay.
And if you're interested, you can search online. There are a lot of derivative of that covariance matrix. So in this case, we need to evaluate the joint distribution to get the posterior distribution. And we can see the advantage of the third method is if you know your data given the classification label is Gaussian distribution or Boson distribution, then you have additional information. Then in this case, you can use the third method and you will get a much more accurate result. But in this case, there's no assumption of your data, of your likelihood function P here, the Px given T. It can be any distribution. So in the third method, you have some prior knowledge. You know the data distribution is Gaussian or Boson. So in this case, if you have very few number of training data and you know your data is Gaussian, then you can generate a more accurate result in the third method compared with the second method. Another problem of this method is if the dimensionality of x is very high, maybe if you have 1,000 number of dimensionality of x, then you need a bunch of observation to evaluate your joint distribution. Otherwise, you cannot get accurate joint distribution. So your method may be not good. So in the case if you have a high dimensionality x, and you don't have enough number of observation, then you maybe try the second method. And another disadvantage of this is you can see there are much more hidden variables here. So here we only have m, but here we have the mu is m dimension, right? And the mu0 is m dimension. And here is m by m plus 1 over 2 number of, and here is 1. So the total is m plus m times m plus 5 over 2 plus 1 parameters. So if your dimensionality of input variable x is very large, then you need to estimate much more hidden parameters by using the third method. So there's a trade-off. So you know the distribution, you know some prior information, and the dimensionality of x is not huge, then you may try the third method. And I will talk something more about the advantage of the last two methods compared with the first. So in the second, the last two methods, we try to compute the posterior distribution. So it can be used in the model combination. For example, if we want to diagnose if a patient has a cancer or not, then one feature can be the X-ray image, and another can be the some test based on your blood or something. So in this case, you may be X1, like from the X-ray image, and this is from the blood test. And if you get the posterior distribution, you can combine those together and make your final decision. But in this case, there's no probability can be found. So this is another advantage. Yes, there's another advantage for the third method. In this case, in the third method, we got pi and the sigma here. And for any input x, we can evaluate y given x on both Gaussian kernel, and we choose the y which has a larger probability range. And if we want to evaluate this term, we need to evaluate the model evidence. So in this case, we know the model evidence, Px. So given any input x, the Px is very small. Then we know the classification accuracy of this x may be not very good. So this gives you a way to reject some input. So this is a very rare case. So in this case, the classification accuracy may be not very good, right? Because this is a very rare case. Like, you know the Px like this, and your model was learned from here. And if some x input x is here, then you cannot trust your output because you are using a rare case, but you train your model based on the normal case. So this is another advantage. They call the rejection method. You can use the P of x to reject some input. And yeah, that's all about the classification of three methods and how you can choose this method and the advantage and disadvantage of this method.